The gravity of the time is such that every new avenue of peace, no matter how dimly discernible, should be explored. Never before in history has so much hope for so many people been gathered together in a single organization. You will provide a great share of the wisdom, of the courage, and the faith which can bring to this world lasting peace for all nations and happiness and well-being for all men.
So we are here today on this special episode of Titans Nuclear with Jake DeWitte, who is the founder of Oklo. Jake, welcome to Titans.
Thanks for having me, Brett. Excited to be here.
Yeah, no, I remember we met like 5 years ago, back in Silicon Valley. You were one of the first people I talked to in the industry, and you spent 3 hours with me trying to get me up to speed on everything. So it's just so great to finally be able to, first be able to watch all your progress over all these years, but also be able to talk about it now. So, yeah.
Yeah, man. I remember you buying lunch for, another co-founder getting started off the ground, and good chat and good conversation. It's exciting to do this. I mean, it's funny because we'd waited like, okay, we should do Titans after, we get some stuff done. This will be a fun thing to do. So I appreciate you having me on here in this kind of context.
Yeah, of course. Okay. So as we normally do on this program, we like to start with the individual. So why don't you tell me about you? Where did you grow up and how'd you get into the sector?
Yeah. So, I had the fortunate experience, I should say, of being born and raised in Albuquerque, New Mexico, because when you do that, you get to be around a lot of nuclear stuff inadvertently, if you want to, even more so. So in other words, as a kid, I just had the chance to be around this kind of technology, people working on it, for as long as I can remember.
What did your folks do? Were they out working at the lab out there?
Yeah, my dad did. He was in the Air Force, and then he went over and worked at Sandia National Labs, and did touch on aspects on civil nuclear use, as well as sort of facilities and some of the R&D capabilities they have out at the lab just for semiconductors and other things. But that got me some early exposure to the technology. So I remember as a kid taking an interest in science and technology, and then going to the National Atomic Museum, which is now the National Nuclear Science Museum. I just fell in love with the place because it was like this crazy implementation of something that felt like it was out of science fiction, but it was real life. Splitting atoms and actually getting energy out of it felt like it was from something that was from a future far away, but we actually had it here. And I remember it was so powerful for me to really, I was in grade school, but when I realized they had an exhibit and they talked to the fact that in Albuquerque, we got about a quarter of our electricity from the Palo Verde generating station out in Phoenix. And I was so excited by that, to think that like 15 seconds of every minute, not exactly, but more or less, right, was power that was from nuclear. And I was like, man, I want to work in this stuff, because it just seemed like the application of science fiction in real life.
Yeah. So, it's so amazing. I mean, it was like, when it first came out, it was like the science fiction-y thing. It's like, what can nuclear do to transform the world? I mean, there's just so much optimism when you go back and look at the early literature. Unfortunately, I think that's something we lost over the years, but hopefully we can bring it back. Yeah. And I think startups are the way to bring it back, right? Like, these are the companies that know how to, craft and curate messaging differently than the old incumbents in the industry.
Totally agree. And I think it's reflected upon the ways in which we approach the technology. It's with that wonder and that awe, right? Like thinking about what you can do with something in an unbridled fashion versus thinking, sort of limiting yourself artificially because, oh, well, that's the way it's been done, so we can't do it differently. I mean, it's so important to have that mentality. And I remember as a kid, I used to get I love the game Simcity, and I get so frustrated because they treated nuclear negatively. So I built fusion plants and was like, no, these are just really fission plants because they work now, and that's really cool. And they don't they don't penalize you for it. And I wrote letters to the people who made that game complaining about that, because it's like, you're doing a disservice, because nuclear is awesome and it's safe.
That's so funny, because I also played SimCity, and maybe I don't remember that. Maybe that part never got incepted into my brain. I think I remember, like you elevate through the different power sources.
Yeah.
The time. Yeah, but I don't remember. I guess they'd have a explosion or something in the game or something.
Yeah, the biggest thing I remember is it would like downgrade property values, and it would induce like radiation around the plants. But then if you built a coal plant, there was no radiation around it, which of course in real life.
Yeah, just kids getting asthma, no big deal.
Yeah, and more radiation from the coal because we
that's
don't
true. That's
it. So I I hated that. And then, you know, I think from that point on as a kid, I just knew that was one of the things I wanted to work on, and basically set out to do that. And growing up there, thankfully, I had those opportunities. So in high school, I got hired in at Sandia National Labs to an internship where I got to have some real experience, you know, working on technology and with, you know, world leading experts.
Yeah, what project were
Amazing
you on
opportunities.
at that internship?
Yeah, so I actually got hired in on the weapons side, and had some experience just doing some support testing on some equipment and components there, but was around these amazing world-class facilities and experts, and that stuck with me.
Yeah.
And then I spent 2 summers there in high school, and then in undergrad when I went back for internships, I actually got to work at their radiation facilities, including their test reactors. And yeah, I mean, that really planted the seed for, I think, or not planted, but that's where the seed really germinated. You know, like I was like, man, this is what I want to work on. This is,
yeah, you're no longer just a little kid fantasizing.
Yeah.
Now you have like real, like you can still fantasize, but it's like with real physical world parameters in your head.
Yeah, and sitting with, and one of the cool things too is working in a real irradiation equipment and facilities, and like actually, and they had great engineers there who like didn't let us get, you know, use codes as crutches all the time. So it was like, okay, we set up these experiments to irradiate seeds to look at, you know, effects in this big gamma radiation facility. And they're like, okay, build a 3D dose map, but don't run like a big fancy simulation. Do it for first principles.
Cool.
And one who gets closest gets a burrito. So you like learn a lot more in the hands-on experience, you know, and then getting to work on reactors and watching them like plot out, you know, a startup or an approach to critical or a power ramp or a power pulse, and actually seeing it and seeing the implementation of, you know, first principles. I mean, that was just, I was like, man, I can't wait to work on things that actually get to touch building things. And that's kind of what set on the journey for leading us to start Oklo.
Amazing. And tell me about your studies as well. How did you like gain your kind of formal training in nuclear, and did you do any like special thing with your master's or PhD program?
Yeah, it was funny. So in high school, I knew I wanted to work in nuclear. I didn't know nuclear engineering was a dedicated discipline in undergrad until like I was late junior year. I thought I was going to do mechanical engineering and physics. And then all of a sudden I was like, oh wait, there's actually nuclear engineering in programs. Anyway, so there was an obvious point I was going to study those things. So studied that in undergrad, had the chance to work at Urenco as an intern when they were doing, you know, setting basically in the licensing stages for their enrichment plant in New Mexico, and then 2 summers at Sandia. And then I went to grad school. And between undergrad and grad school, I spent a summer at GE Hitachi working on their PRISM reactor design. And then in grad school, my master's work was on basically passive shutdown systems for sodium fast reactors. And then my PhD work was on making today's operating plants bigger, like so very large uprates, as well as long-term life extensions, coupled in with, you know, some cool things you can do to help achieve those goals. You know, one of my favorite statistics coming out of that place, you know, did my graduate work at MIT. At the time, they didn't have like they had all these, the Energy Club had all these like they had all these energy communities around everything but nuclear. Nuclear didn't have one. So I was like, we got to change that. So we set one up, and it was so fascinating because so many people were so curious by it. And it was neat to see kind of this changing attitude, right? And I don't, at the time I would say like, nuclear was a little underappreciated by MIT and the institute there, and I think now it's really started to change, which is great. Not by the department, of course, but just by the broader community. So it's been neat to see that kind of evolution since then, and the fact that people start to wake up and realize, like, oh wow, like those existing plants provide 20% of our power and well over half the energy we make. We've added like what 7 or 8 gigawatts of new capacity just through uprates. It's amazing stuff, you know. And now we have all these new technologies and new approaches to doing this stuff really efficiently. So, you know, it's a pretty exciting era to be thinking about this stuff.
Yeah, it's pretty incredible. I mean, even from the time that I started, you know, doing the podcast to now, I've just seen, I mean, especially in like the last few weeks, but in the last couple of years, the appreciation for nuclear, huge uptake. And it actually troubles me because not troubles me. It's a great thing, but it troubles me to figure out like, how did this, like, what was changing the cultural tide? Were there specific events? Was it a general, you know, climate forcing function that, or like, do you have any ideas on why this is?
I think there's great books to be written on this in time. You know, because I think it's still evolving, but I think what you hit on was a big one. I think one is the climate considerations. I think there's such a shift of folks who are like, we really need to do things about climate. And when they look at the data and now, thankfully, right, this sounds hokey to say, but a difference now between where we were maybe even 30 or 40 years ago is we live in an age where information is so readily accessible. People can do their own research and come to the conclusions like, oh, wow, like nuclear is the way to do this. That's pretty cool. And then I think on top of that, there's a generational shift, that I think affords people who really want to work on challenges like us that make a big difference for humanity. And also having blueprints and roadmaps demonstrated by companies in other spaces that are in sort of the hardware space that have shown you can do new things and be successful, a la SpaceX and Tesla as easy examples to point to, among others. That it's really hard work, but it can be done, and I think that's really created a neat, I think, environment, that allows people to really look at this and be like, hey, nuclear makes a lot of sense, and there's better ways to try doing it than we've done it in the past, then we should try those things.
Yep, absolutely. It's just so funny. I'll just a quick little aside. I keep asking this question, like, what's causing this shift in public perception? In like one case, it's pretty easy. In case of the Netherlands, there was like this Dutch comedian who went on. Do you remember this? Like 2 years ago,
I heard about it.
Yeah, the video is being sent around. He does like a John Oliver type skit. Where he talks about how like, it's so obvious, but he's able to do it in like a funny, sarcastic way. Like the problems aren't that big problems, which is so much better than being defensive, to be like funny and sarcastic about it. And like the public opinion just shifted in the Netherlands, I think like overnight, seriously, overnight. It was incredible. And so now I'm trying to figure out, well, like what could we do to apply that here? But unfortunately, the real John Oliver, like around the same time period, did like an anti-nuclear waste, like really alarmist around nuclear waste. And I'm like, God damn, such a missed opportunity.
Yeah, it is true. I mean, I should say too, what I just answered with, I think is only part of the reason. There's so much more going on. But like you said, I think you're right. There's some really significant opportunities for folks who can wake up and see these things. Like I thought it was interesting on TV. I remember, what was it, a couple of years ago, maybe 4 years ago, Madam Secretary was the show, and they had like a whole special episode highlighting like we were all wrong about nuclear kind of thing and being focused on it. I agree. I think more things like that are going to change that, and it would be so cool to see some of the major, like, I would say comedian, like, what's the right word? I guess I'd say media influencers to really just talk about this, talk about the facts, because it does make a difference.
Yep. Okay. Sorry for that little aside. Let's get back to your story. So how did you? Was it in grad school that you had the idea for Oklo? Was it after you graduated that got started? What's the story behind it?
Yeah, it was an idea that started floating in my mind late in undergrad. So sort of like mid to late 2000s, did our undergraduate design project and saw sort of what it was like to be working on a small team doing like cool work. Obviously it was a school project, but I really threw myself into it. And I was kind of thinking like, there's so many cool things you can do with different business models and different technology approaches and sizes of technologies than seem to be done in nuclear at the time, that maybe it'd be interesting to explore that. Mostly I thought of it through like joining activities that were already in progress in the space. But as I started to like learn more about what was going on, I didn't see a lot going on that was really trying to tackle some of the problems from a way that I thought was worth taking a shot at doing differently. And that just sort of, I would say, built up over a couple years into grad school. And then eventually come about 2012, 13, it started to be like, hey, there's some meat to trying to approach this with a very small reactor design that kind of mimics a little bit on Tesla's strategy of building out kind of a niche product to start on the Roadster, and then using the experiences gained on that to then scale to, sort of an array of sizes. I still lean on the smaller end. I think, as you see too, like there's a lot of flexibility that comes from that, but can open the door for some interesting deployment scenarios and models, as opposed to trying to go in and repeat the same process. And I'm not saying this to criticize it, but of sort of like building up an idea, trying to get a bunch of government funding to do it, and then implementing it and taking decadal timescales to do things that ultimately end up straddling. You're just adding a lot of, baggage to your process because you kind of end up having to answer to a lot of masters, to put it that way.
I think I like that decadal. I've never heard that word used quite that way, but that's perfect. Yeah, decadal timescales. I love that. I think that model doesn't work because like there's a human element to like getting an entrepreneurial thing up and running, and people can only take so much for so long before they lose their enthusiasm. I mean, startups can take 10 years to build up, but not 20. Like the original people are gone, the culture is gone. Like you can't wait that long.
No, I agree. And you just lose too much, if it takes that long, and you lose enthusiasm and support. So,
and so where did your like entrepreneurial spirit come from? Because most of the, the PhDs that I meet in the nuclear world, that's the only way they think is government grants. What made you different?
I don't know. I wonder that a lot. I would say I probably wasn't like by classical definitions, the great, like the classically like loved grad student by their professors. I definitely like to challenge things, and I definitely did things in different ways. Largely because I was just drawn to like seems like there's a better way to do this. Why don't we try a better way to do this? Or there seems to be a much more efficient way to do this. Like instead of maybe some theater involved to doing something some old way and trying to do it that way. In many ways, like it's funny because I've long thought like, well, why did I end up getting, why did I go through grad school? Because I wasn't really drawn to do academic work. I mean, I was interested in the research and I was interested in the technology, but it kind of felt like because that was all there was to do at the time. And so like something I always think about now is like, man, if an opportunity existed like there exists today, I definitely would have gone to grad school. I would have gone and worked at some of these companies doing the things that are going on today. Not to say grad school is bad. I mean, it can be great. It's just like, I think in general, like I was always drawn to looking at these things from a lens of how can we not do things differently or more efficiently? I mean, in undergrad, I was the kid who'd look at like, what was the minimum amount of work I needed to do to get the minimum grade I wanted to get, right? So if I only had to do half the homework to get an A, then I do half the homeworks. I don't know.
That's the engineer's way. Yeah.
Yeah. And so I guess I was just always drawn to like, what's the right way to get that done? Because I wanted to focus on sort of like iterating things more quickly and thinking about things in the sense of how do we move towards productizing stuff a little faster and not just being stuck in endless loops of R&D, which R&D is really great because it advances things, but I wanted to get more into like the branching it into what's neat. And what was interesting for me was it was kind of a realization that was a departure from what my experience had been in grad school. And I had to come to terms with this, which was like when you're taking something to market and out of product, it's often like some of the more boring stuff compared to what you're doing in a lab, because the lab stuff's cutting edge, unknown, a lot of neat stuff. And it was when I realized that I really love some of the aspects on the boring stuff, because that's what actually involves like getting metal made into things you use. Like that's kind of what led me to, I think, want to do that and tackle that. But ultimately what drove me was I just kept getting like sort of laying awake at night thinking that there were better ways to tackle bringing nuclear technology to market, and it was too important to wait and too important to try doing the same things over and over again that weren't working very efficiently. I mean,
but how did you even know about private capital sources at all? I mean, I wouldn't have known about this. Like, had I not gone to school out in the Bay Area, like I wouldn't have known how you even approach private investors. How did you know? Did you have a friend? Did you watch Silicon Valley, the TV show? Like, how did you figure it out?
Yeah, I didn't know much about it. I generally was like, oh, venture capital, I don't know. It seems like something, and seems like it would be like it's really short term and focused on software only. When I was like early in grad school, I wasn't really thinking that much about it at that point. But as I started thinking more and being around the MIT ecosystem, thankfully there's a pretty healthy, like, I would say startup scene around that. That's a really silly way of describing it, but there's a pretty healthy ecosystem there.
No, that's important. That's really important.
Yeah, I mean, just getting the chance to go to different things and take classes or listen to seminars and see people who like VCs come and talk about things, and you start to. And at the time too, they had a lot of work. When I started in grad school, right, that was at kind of the peak of the clean tech bubble, like I would say. So there's a lot of activity around, venture spinning out in batteries and solar and all these other things. So you kind of start to see it. And of course, to me, it stuck out. There was nothing in nuclear. It's like, this feels like it's missing the mark for obvious reasons. But that's when I started kind of learning a little bit about it. When we started the company, I thought, oh man, yeah, like we'll raise a seed round of like $20 million and then we'll go from there. And then, then I learned a little more and was like, oh, okay, yeah, you don't just raise a seed round of $20 million.
Some people do. It's crazy, but yeah.
That's true. But what really started to cement it though was like, kind of had a sense of it. 2012, like, okay, it seemed like that was the pathway to go. 13, we started thinking about how we would approach it. And then, happen chance, randomly, I'd say in April 2013, right when Oklo was just a fledgling idea, sat across the table at a dinner from Sam Altman and had the chance to just talk with him. And, he was really interested in nuclear at the time and was looking at like the problems from kind of a similar mindset. And he became like a really good friend, mentor, advisor, and investor, and then board member to help sort of think about this stuff and be a really good sounding board from someone who had very little experience on my end to someone who thought a lot about this and came from a deep tech experience background on it to sort of bounce these things off of.
Did Sam have to be convinced of nuclear, or during that meeting, had he already had the idea in his head that nuclear is kind of an interesting space?
Yeah, it was interesting. So like he was already convinced. We just were sitting.
Did you ever ask him how that happened? Because I was out in Silicon Valley around the time that he rose to prominence, and there was no talk of nuclear in the Bay Area at all. Do you know where he first was convinced?
Yeah, I'll paraphrase it simplistically. Obviously, he could tell the story fully, but basically, he was looking at it from the sense of, you know, energy. And it's as he was kind of diving into the space and the technology, he realized how important nuclear was and how scalable it was, and how a lot of the, I would say, there's a lot of untapped potential because so many things were being done in this kind of, I would say, kind of classical way or conventional ways, and there hadn't been a lot of innovation in terms of process, business model, technology.
Okay, so it's just like a first principles. He derived it
Yeah.
himself from looking at the landscape.
And then he dove into it and kind of realized there were pathways to be successful in a venture to do it, looking at it by starting kind of smaller, trying to focus on metrics of getting a product out to market as quickly as you can.
Yep, I think it makes total sense. Okay, so let's talk about that product. Like, what did you cook
Yeah.
up?
Yeah, so like the idea we really looked at was, you know, starting small with the sense of like, what does it look like to build? I mean, basically kind of a, I don't know, a minimum viable product as we used to think it was, terminology we got to learn and from sort of being around that scene.
I think it's a fine way to describe it, yeah.
Of saying like, what's a small reactor that has a market, that's a way we can get sort of things set up in place, get through the regulatory process, get infrastructure established, and then get experience and then start iterating, right? But how do we iterate? And not require billions of dollars just to build the first plant. And that's what kind of set us up on coming up with a small system that was on the megawatt scale. We approach this from a technology agnostic perspective and try not to be like, you know, one of the things I'd seen in academia was, hey, this is my favorite technology, this is what we should try to pursue, it working and everything. Instead, it was like, hey, what's the right fit of features and of maturity to get the door?
And so, yeah, so if you could just describe what the technology was, but also I'd love to hear the rationale as to why, looking at it from a technology agnostic perspective, you settled on this combination of, you know, materials, coolant, moderator, fuel, et cetera, et cetera.
Yeah, so we basically set out to sort of understand, okay, what are some of the neat features a small system like this should have? You know, long fuel lifetimes to avoid having a lot of on-site refueling, having a pretty a reduced complexity in your control system. So, you know, having something that has a pretty, to use a technical term, like a pretty flat reactivity letdown, something that has you know, I would say like kind of the obvious inherent and passive safety features built into these systems by design, and something that operated at low pressures at those sizes was important. So that kind of led us to sort of down select to building on the legacy of liquid metal cooled fast reactors, in particular because of sort of the combination features they afforded on that front. So, you know, sodium coolant based technologies, metallic fuel is demonstrated by EBR2 and other programs, using pretty conventional stainless alloys to support that, not driving the fuel to extraordinarily high, you know, burnups, not trying to push the envelope so far in performance, but rather achieve what was needed for economic objectives. And that also checked the boxes.
Just to slow down for some of our audience, because you went through a little bit fast, a liquid metal cooled fast reactor. Can you just break down maybe each of those, just kind of slow and like we're 5 years old? Like, what is each component of that mean?
Yeah, so liquid metal, you know, it means cooled by molten metals. You know, one analogy sometimes I think about is maybe it's not the best one, but I think it was Terminator 2. They had that like liquid metal robot dude. So I always think of liquid metals, I think of that. Anyway, it's not, you know, sentient liquid metal, but liquid metal coolant. So like sodium is the one we're using, but there's, you know, you can use sodium and potassium alloys, you can use lead bismuth alloys. Historically speaking, there's other ones you can look at, but basically the nice things about liquid metals are they're really, really good at heat transfer, and they can operate at fairly high temperatures, and they don't need to be pressurized. And the good news about why we like sodium is there's a lot of experience around it. We know how to handle it, we know how to design around it, and we get benefits of making things pretty compact, like heat exchangers and other things like that. And then on top of that, it's, you know, it affords you to be a fast reactor, which is something we've been interested in for the fuel cycle benefits. What that means is, right, when you split an atom, you release a couple neutrons. Those are born going quite fast. And in a fast reactor, we don't slow those neutrons down. In today's reactors, we slow them down by bouncing them off, you know, moderating elements like hydrogen and water. The reason you don't slow them down is it makes it so that you can do some cool things with the fuel. You can be very fuel efficient. You can even recycle fuel as waste. And it has some great safety features. The downside is you need more fuel, right? So, but the other nice thing is you don't poison the reactor as readily by the byproducts of the fission process. So it allows for some pretty neat things in terms of how you can manage and control the reactors, how you can simplify aspects of design, how you can achieve really long lifetimes because of the physics of it. And those were some of the features that we were attracted to that kind of built on, you know, previous work that looked at small fast reactors that were sealed up and would run for like 20 years on a single load of fuel. So that's kind of the
What are
fundamental.
some of the challenges that are inherent to fast reactors? Are the neutrons more likely to escape your system altogether? Is there a problem with that?
Yeah, so it's interesting. You have a different kind of design game for the neutron economy, if you will. So the balance of neutrons, they're definitely more likely to escape. You can use that to your advantage with how you design the system from safety perspectives, but you can pay for that as well for fuel performance. In other words, how much energy you can get out of the fuel before you have to replace it. Thankfully, because of some of the attributes also of how fast neutrons interact with uranium-238, you can also offset, right, some of the fission of fuel you produce by producing other fuel forms like isotopes of plutonium. So that's where breeder reactors can be developed. But you can also just do things that have very basically not breeding per se, but replacing pretty readily the amount of fuel you're consuming by producing more fuel, but maybe not quite as much as you consume.
And is this fuel like mixed in with the coolant, or is it in separate rods like a traditional reactor?
Separate rods like a traditional reactor. But you can make fast reactors that have the fuel dissolved up in the coolant. The one thing that is interesting to me is one of the ways in which we think about economics for new plants to be competitive, and something I've seen you talk about, right, is sort of right sizing the safety envelope with actually what matters for safety, right? Like what functionally actually matters. And so with some of these systems, you can really reduce that because you put the sort of physics of safety inherently into the reactor, and having the fuel sort of in these separate elements allows you to have those boundaries in place, and it allows you to not have to have sort of safety envelopes around all the places where the fuel would circulate. That was one of the drivers for us to kind of build on that technology. One of the other hard things about fast reactors, though, with that is the damage the neutrons can cause, because they are moving really fast. You need more of them, and at the end of the day, they bounce atoms out of the structures that they're in. So for us, we just run at lower power densities, and we don't push that edge.
I think that's very clever. I think that's not only clever, but it's hard for an engineer to develop the discipline to not always be optimizing every system. It's kind of like built into us. So just to kind of hear you say that and repeat it, like, hey, it doesn't have to be it doesn't have to be the highest performance system. We can back it back down a little bit to gain. So I just love hearing that.
Yeah, you don't need to build a Ferrari when you need to just build a Chevy or a Ford. So,
and then were there any challenges kind of left over from those early programs? And I'm also curious about the power system itself, even more than the reactor. Was there anything that you have to develop? Is there a market for things to help move liquid metal around a system? I don't know if it's a pump or if it's just a heater to keep it liquid in some places. Is there a supply chain for that type of stuff?
Yeah, so it's interesting. I mean, at the end of the day, the supply chain, exists for most things, but not for everything. But there's also a lot of incremental improvements on where the supply chain exists that you can sort of build on things that exist, and specially tune them without having to customize the supply chain for a lot of the parts. That's another reason we're kind of.
Give me an example of that. You mentioned stainless steel. Does custom tuning stainless steel just mean, hey, let's have a little thicker stainless steel so it can resist corrosion? Or do you mean you have to go to a stainless steel alloy company and say can you give me this tweak on the alloy chemistry?
Yeah, it's really just about hey, we design it really to be within specs of what normal stainless steel 304L and 316L components are off the shelf, including tubing thicknesses and also vessel sizes. There's a little bit of customization on the vessel and the internal attachments, just because that dimensions are they're optimized for the nuclear aspects, not optimized just for commoditized components. But we do optimize towards what's readily available, right? If you need to go customize a bunch of pipe, it gets a lot more expensive, right? Or tubing, versus just saying, okay, maybe I'll trade off a couple % in performance in terms of power output, but use something that already exists. And at these sizes, that really starts to matter. Now, in time, if you build more of these reactors in volume, then you can start to customize as you want, right? Because you can pay for it. But
I agree. I think your strategy is just dead on.
But supply chain is the hardest thing. I mean, I think it's the hardest thing,
Well, so tell me, so what supply chain issues have you run into and overcome already? And then maybe what are some that might still be on the horizon?
Yeah, I mean, sort of the stuff we're just talking about, really trying to focus on what exists in those existing alloys, bases, and components that already exist. One of the things we like to think about is you think about the vessel or the tanks our stuff fits in. It's a lot different than big forged customized vessels. And you change the cost paradigm considerably, right? You can build on stuff where there's hundreds of suppliers just in North America alone that can make these things, and all of a sudden the costs go from hundreds of millions to hundreds of thousands. I mean, I'm being a little bit facetious on the numbers, but it's a significant departure in terms of cost savings by building on stuff that's being made readily available today. Similarly, we made some decisions on the design to not need really exotic things on like the pumping side. There's some cool technology to develop there, but we'll get to that later. We'll see how that develops separately. Pushing forward brand new componentry is just, it can be fun, but it's not core to our business necessarily. So it's a distraction.
Does your does your system need pumps? I remember at some point it was advertised as like a heat pipe, or is that still the case?
Yeah, so we basically look at the configuration of it. At the very small sizes, you have heat pipes, and then if you get at a bigger size range, as you scale it up, you basically open up the heat pipes. In other words, it becomes a convective pool. So, but no pumps, pumps. So at the smallest sizes, it's just a heat pipe cooling. And then as you increase the size on that, you go to just a natural convection liquid metal system.
And is there good software to help model that type of, I mean, are there other heat pipe systems that exist in the world that you're able to like piggyback off of their work to understand how these systems perform, or where they might fail or break down, or how you can, design, because like even like the designing of like normal pipe systems in just any like power system, like you got to put an elbow in the right place, and like you got to allow for like expansion and stuff. Is there like a pool of is there another industry that uses heat pipes all the time that you can learn from?
Not there is. I mean, in consumer electronics, really, there is a ton. It's not, they're running at lower temperatures, but it's the same general physics, and it's actually way more exotic than what we're doing because they have all these weird bends. We're just straight tubes. It's a lot easier, and we're gravity assisted, which also makes things simpler. So all that really helps us build on that. And then on top of that, there's been some cool work for really high performance development on sort of the renewable side. But at the end of the day, we're not trying to push the bounds on performance there. We're just living well within what's been done and what's demonstrated, really just trying to drive simplicity. Actually, we back away from the highest performance stuff because we don't need it and it costs a lot more to make it.
Yeah.
And
a lot of unknown unknowns there. Yeah. And then, okay, so that's your hot rock. So what's the rest? How do you create electrons?
Yeah. And then after that, basically you're transferring heat ultimately to a power conversion system that's spinning, right? So spinning turbo machinery. Steam ranking is the predominant choice. We're doing some work with supercritical carbon dioxide, like in the intermediate term. Like it's pretty cool, but I think at the end of the day, like that's going to be something that takes some time to develop, and we're not a power conversion system developer.
Right. Don't take on two technology risks at the same time.
Yeah.
Okay, so you guys are going to go with steam ranking
steam ranking
early on. All right, that's smart. Yeah, great.
Yep. And it builds on, it's a little different, right? But the steam turbo machinery generally exists at these configurations and these sizes. And thankfully the temperatures here are pretty similar to the steam turbo machinery at these sizes, because it's usually used for fossil combustion, and these are higher temperature systems than light water reactors, but they're not as high temperature as some of the like really big coal or fossil plants, right? So it doesn't need kind of that kind of stuff in there.
Anything else with the technology that you want to share that might be interesting to our audience? And then I got a whole bunch of business and regulatory questions and the good stuff.
Yeah, I think the other interesting thing that's really fun about fast reactors is what you can do with the fuel for recycling. Like at the end of the day, this is something that's always fascinated me about the potential. But the challenge has been how do you get the sort of what comes first, right? It's recycling or reactors. And our view is get the reactors out the door where there's a market for them, and that's going to pull the fuel behind it. Because that's one of the hardest parts about the supply chain is the fuel.
So what's the plan on fuel right now? I know you guys did an argon collaboration that came out recently. Is that what's going on there?
Yeah, so we're using uranium zirconium alloy, so building on a legacy of fast reactor fuel forms. We've done some work casting different fuel elements with Idaho dating back at this point 5 years ago. And then as we work with them for our first unit, we're setting up basically a pilot fabrication facility at Idaho, where we'll make fuel for our first core.
Uranium zirconium, is that what the HIFER reactor uses at Oak Ridge? Or is that something else? I know it's like a metallic uranium, some sort, I think.
Yeah, I think HIFER uses like uranium aluminum sort of like thing, but I could be wrong on that. But yeah, uranium zirconium is basically 90% uranium, 10% zirconium, the fuel form that was really developed in the sort of integral fast reactor programs.
And can you buy that blend from, like, how do you get them to make it into the form factor, or who even mixes uranium and zirconium together right now?
Yeah, so we do at our fabrication plant. So what we're going to be doing. So in these crucibles, we take the uranium chunks and you mix in the zirconium chunks, and then you have sort of a casting regime.
Yeah, really like a metallurgy. You got like a metallurgy shop going. Wow. Okay.
Yeah, well, Yeah, I mean, at Idaho is where,
Yeah.
is where that gets set up. But it's kind of neat because they've been making this stuff for a long time. They have a lot of experience with it. And part of the reason we went this path is because they have those capabilities and they have some facilities that we can just expand that capacity to do it. Now, longer term,
yeah.
we're going to want to set up, bigger scale capacity, including possibly working with different vendors that can do this. The nice thing about making metal fuels, it requires a lot less space than making today's oxide fuel.
You can't just
so that
hire
can be
like
beneficial.
doesn't BWXT do this for the military or something? Is there any way to just hire them to do it or anything and take that off your plate?
Yeah, I mean, there's definitely options for stuff like that. In general, they don't make exactly this form. And in general, you've got a lot of extra capabilities that they have, like being a category 1 facility that does all this really exotic stuff that we just don't necessarily need.
And what do you need? Since it's not activated at the point of fuel forming, are there any special precautions that you need with like your systems and equipment to handle it, or is it totally cool because it's unactivated?
Yeah, so it's funny. Fresh fuel would be normal, but so the fuel we're using, we got a fuel award from Idaho that provides material for the first core, and that material is actually used in this reactor EBR2 that ran for 30 years in Idaho. That's sort of the predecessor technology, or in some ways like the original technology on which we're basing a lot of the things we're doing. So that material does, in its recycling effort that Idaho's doing, it does carry some impurities, contaminants over. So we do have to do this work in glove boxes. But it also positions us well to then be able to use that fuel and carry those experiences over to the recycling front, which is kind of something that like longer term is where we see a lot of value. Because one of the things that's been really exciting is with these with fast reactors in particular, you can accommodate a much messier fuel source. In other words, when you pull out, basically the unused fuel of today's used fuel, the transuranics in particular, you can use these advanced technologies called pyroprocessing or electrorefining, keep them all mixed up, and then fabricate new fuel for fast reactors. And fast reactors can accommodate that kind of being a pretty messy mix of things. So it's radioactive, it's difficult to handle, which is great for security and safeguards, but it also means a cheaper, simpler process. And this actually inverts the economics of recycling on its head, because then you can produce fuel actually more cheaply than fresh fuel. And it's something we're really excited about, which is why we've been working with argon. Now, this is longer term. This is stuff that takes a long time to develop. So, we're working with what we can do with today's fuel sources, both fresh and lightly used recovered research reactor fuels. But long term, that's the thing we really want to get into, also for our use, because at the end of our lifetime, we've still got a lot of useful fuel in our fuel that we want to be able to recover, reuse again. And I think it actually offers a really attractive way by which we can help alleviate sort of the economic burdens on the on cost on used fuel disposal, and just makes it much more amenable to alternative solutions that are pretty cool.
Cool. Great extra feature there. Okay, can we switch gears for a second? I want to hear about the business model, in the short term, medium term, long term, maybe just a few thoughts on that.
Yeah, so what we've kind of, one of the things we've learned on the way here is to try the things, we swing for the fences right away on things in many cases, not necessarily on the things that are very, very costly, but for the things that like we think are important to try. So in other words, we're trying to solve some problems about what we see as market adoption challenges for what we're doing. In other words, when you think about reactors that are sort of on the 1.5 to 15 megawatt range in size, the market case for that in many ways looks a little bit different than for a gigawatt plant. In other words, you get a lot of smaller utilities, you get a lot of even direct industry, consumers that don't necessarily want to own and operate a plant. So we do that for them. We just consign power or sell them power through a power purchase agreement or similar mechanism that puts all sort of the ownership and financing burden, everything else on us. But that makes it a lot easier for folks to adopt what we're doing. We thought we'd have to walk our way into this, but that's one of the things we learned was like, no, just go all in for it, and then learn and iterate from there and what works and what doesn't work. And that's what we've really tried to do. So we found that has a lot of traction with a couple different kind of groups, especially on sort of the industrial user side and smaller utility side. And it has some pretty cool features for utilities looking at how do they replace partial ownership in coal plants that are retiring. They don't need to replace it like with hundreds of megawatts, but they need to replace it with tens of megawatts, and we can be well suited to do that for them.
And this is you're operating in the domestic markets, right? This is like US customers that you're talking to primarily?
Mostly, yeah, but we're also looking internationally in some cases where we see some inbound interest based on some of the stuff we've been doing here. And similarly, we see a lot of features for how this can work especially for sort of industrial users, sort of internationally, and then even some of the way the grid's developing internationally, where you can sort of add some significant decentralization and grid resiliency through systems like this. You think about what we're doing. you can have a reactor that makes up to 15 megawatts of power and runs for 10 to 20 years without refueling it. It's a great way to sort of, without emissions, right? A great way to have something that can provide grid stabilization.
Yeah, I mean, especially for like island nations around the world. I mean, it's like, you look down at the Caribbean, it's like, okay, why doesn't every island have 1, 2, 3, or 10 of your, depending on how big they are, of your reactors, and just not, I mean, you could fortify them to make them hurricane resistant.
Yeah.
And then you could, so you're solving one problem for them, and then the fuel cost and the fuel delivery, and they want to be clean. Like, these are like pristine beach environments. Like, they love the clean idea. So it seems to me like there's a huge opportunity there. And then I'm wondering, and this is going to be my next question. It's like, one of the things that we learned early on was that, one of the biggest burdens for bringing nuclear to market is the regulator, and you got to kind of choose a strategy, because it's going to be a big investment. So yeah, do you do domestic? Do you pick a country internationally? So can you talk maybe through some of your early thought processes there, where you ended up, and then what your experiences have been like?
Yeah, so we focused on the US early on. We saw that as sort of like, what do people call it, the gold standard. We thought it was, hey, that's the one to run into and try first. We also had the pretty strong conviction based on early interactions with them that while it's a difficult process, there are some things there that you can get things done. In other words, they're a regulator that actually has quite a bit of, counterintuitively sometimes to folks' perspective, have quite a bit of flexibility, frankly, built into their process to accommodate new designs. Something that we didn't find in necessarily every sort of established regulatory environment in the world. So we leaned into that. We became the first sort of this wave of advanced reactor developers to engage in pre-application with the NRC in 2016.
And can I just give you a high five for that also? Just like that, no, because seriously, like that's bold. I think you guys have been bold along a bunch of fronts, but to just kind of go at it, like, total respect.
Yeah, I remember sitting on a plane with Caroline, my co-founder, and we just sat there and we were like, the hardest thing we have to do is regulatory, basically. So like, I mean, in terms of what's the main gate. So like, let's just do that first. In other words, let's learn the most and like see what works and doesn't work as quick as we can, and not be afraid of it, and realize that like, it's hard work, but you got to do it. And so we did. And I think one of the things that really came out was we took a pretty original look at this. We were able to bring in some folks who helped, kind of read the lay of the land. But one of the things we always kept coming back to was so many things were being done in the regulatory space, or so many paradigms and so many sort of experts out there had a strong perception that things had to be done the way it had been done for large light water plants. And we saw the writing based on early successes, which, from like NuScale and some of the small light water folks, that, hey, there are some ways you can try these things differently. We just decided we'd try to take it to another level. And so we went, I'll say, we had great engagement. We had a lot of, like, I think, very productive conversations that dove into some very tricky topics, like really small reactors with, small staffing, and just very different, considerations, things where, it wasn't even clear how the regulations exactly apply. So you got to get into that work. That led us to then having engagement from 2016 through 17 and 18. We actually piloted an application kind of with a whole new structure and approach that didn't follow the traditional model. In other words, there's guidance out there for how you develop a power reactor application called New Reg 0800. That's built for large light water reactors. It really didn't make sense for us. So we worked with the NRC to put something together completely differently, completely original. Went through audits with them, got a lot of good feedback that they could handle something really differently. And then we set out to submit that application in 2020. So in March of 2020, we submitted an application to, build basically what the NRC called a custom combined license application. In other words, a license to build and operate a plant using Part 52, which is one of the regulations you can use to do this. Got it in, and something looked totally different than what the NRC had ever seen before. And we tried some really new things, and so we got it accepted, and that was pretty exciting. We got more or less 22 months into the review, and then early this year, NRC came and said, hey, we're going to deny the application because we need some more information. So we were obviously pretty disappointed by that, but at the end of the day, they basically were like, hey, we need this more information, come back and we'll resume the application where we left off. And it was like, okay, that's what we can do.
And yeah, I mean, there's only 2 times that my nuclear heart sunk in these last couple of years. And that was, when I heard the news about the application being denied, and then the Turkey Point thing, that really was tough also. But tell me a little bit about because I know there was this like you were going to be able to do it in like 3 years or something. What happened with that? Did the clock restart now, or do they they just need more time, they need more information? Get me a little bit more about what you think their perspective was.
Yeah, I think their perspective is both. I think at the end of the day, we're doing something really new. And we also were doing it during the middle of a pandemic. We literally submitted our application on March 11th, 2020, which was the day this was, the pandemic was declared a global pandemic. So like that changed everything. And we were built entirely for our reviews to be in-person audits, which obviously all that went out the window. Yeah. So immediately we had a deficit in terms of our planning for how we were going to accommodate all the different things that were going on. Not to mention, we can all be, people did a lot of good work at that time, but there's a real human toll that was going on in 2020, right? In terms of like emotional states and everything. And we were all going through different things. So I think that set us up in a way that was a little bit hard to sort of climb back out of in terms of communications and information exchange. But, I think we made progress on it. It's just at the end of the day, yeah, I think time became a challenge, and the NRC wanted, the novelty of this design and this approach. The NRC wants to see some more information around it, specifically some more examples, I think, and some more like things to point to that in some ways can be looked at sort of outside the application review, so more generically in some cases. So, you kind of have to deal with the blows that you get, but that means that right now, one of the things we can do is be engaging with them to sort of go through those things, illustrate the processes and approaches we took.
So how does it affect your timeline? What do you think the new licensing timeline is going to be?
One thing we've been really encouraged by from NRC management has been, we're not losing the stuff we've done, right? We're not starting over from scratch. What we can do is we can close out where there's some information gaps. And to talk about this too, right? We did a lot of good work with them. I mean, we submitted something that people thought was impossible to submit the week before we submitted it. We got it accepted, and people thought that couldn't happen. And those are testaments because we try new things, and there's some real traction that we had. And so I just think of that as the first iteration. This is the second iteration, and I think we have a pretty clear path to getting done on this. And a lot of it really just distills back to some information that, I would say in some cases is maybe additional information about the design that wasn't part of the normal safety review because it's not relevant for that, but it helps the NRC see it. So, okay, we can work to do that.
Can you offer any specifics there just to maybe even help some others who might, once again, I think you guys are such incredibly courageous for like paving this path. And I hope that you pave the path for others. And I know that you feel that way too, that it's not just about you, it's about you helping all the other designs get through as well. So can you maybe offer a little bit of tips? What types of information did they want more of that others can be prepared to think about ahead of time?
Yeah, there's a couple of things. I think some is on aspects of the plant that aren't, there's an interesting balance here, but some parts of the plant design that aren't relevant necessarily for sort of their safety review, but are part of the technical performance, like just the overall engineered systems of the plant that help them just understand the systems better.
Like a power conversion cycle or something. Like you got to show them the whole steam turbine, not just say, hey, one's going to be here or something.
Yeah, so examples like that and the balance of plant connection there, and then some other aspects on sort of like how other things in the plant feed into and connect to, to either the reactor module or the power conversion system. It's a tricky thing, right? Because like you don't want to get into a world where you just give them everything and then the regulatory scope starts to open up. That's one concern we've heard from previous applicants.
Yep.
But we also have to recognize that this is new. So we want to work with them to make sure they can understand it fully and they see it fully. One of the nice things about really small systems is it's pretty easy to grasp because there's just not that much there. So we can take, we can work with them to help them understand that. Also additional information about, parts of the plant that as we look at things, we did bring forward new methodologies, if you will, like about how you classify parts of the plant based on sort of what's required of them. And also we brought in some aspects for basic, effectively how we do event selection, because this isn't a normal light water reactor. It has different phenomena of interest for sort of scenarios that you have to design against. So how do you screen those for what's credible and what's not? And that's a tricky thing to do with any regulator. I think one of the challenges with the NRC is unfortunately they haven't necessarily had the full free reign and guidance from Congress to help them balance like perspectives on all like external risks as well. In other words, I'm sorry, not external risks to nuclear plants, but like the risks of not building the plant, right? Because
Sure.
if you don't build these things, you build fossil
Well,
plants.
yeah, I mean, I think that's part of the fatal flaw of the industry is that, we're regulated under a set of rules that don't allow an acknowledgement of like cost, benefit, trade-offs, and looking at broader scope of risk. It's really all about radiation risk, without considering any other type of risk in the world.
Yeah.
which I think is it's almost like a real fatal flaw to how the industry has evolved over time. Hopefully not fatal, but it's been a problem.
It's a
But,
challenge.
yeah. But maybe just to get a little bit more specifics, I know like this is like talk of the industry. It's like, so what are you going to do better? What could you have done better in terms of like communication wise? Is it like they ask you a question and you got to answer it within 3 days and it took you guys 5 days or something? Is it simple as that? Or is it like you pushed back too hard on the front and you said, no, we're just not going to answer this for you. And they're like, okay, well then this application's going out the window.
Yeah, so it's funny. So we responded to all the requests on time. I think one time we asked for a couple day extension just because of the timing with like holidays and other things we answered.
What is the expectation when they ask you a question like, hey, can you explain better to me like how this, sensor integrates with this mechanical system? What is the appropriate amount of time to respond to that? And what material do you respond with? Is it a written explanation? Do you have to show schematics? And like, how long do they give you to produce those schematics? That type of thing.
Yeah, usually the normal thing is about 30 days. And then, yeah, it's usually a written response that goes with like, if it's schematics, you include schematics, it could be a written response. It includes analyses, like, calculations, things like that, depending on what the question is. And then there's also audits, which are live time and you're getting them, they're asking questions, you're answering them. And then if there's follow-up, maybe you have another audit or maybe at least more questions, then you report out on the audit. In general, we had really good success with the audits. We answered the questions and generally we got positive traction, what we answered. I think what happened, where they come into effect was largely, there was some information that I think they had a hard time asking the questions they wanted to ask for various reasons. And I think we weren't able to bridge that communication in that time frame. And I think at the end of the day, there was also some, like, in other words, sometimes they were asking questions, we were answering what we heard, but it wasn't what they were asking. And then we had a hard time clarifying that with them. One unfortunate thing that sometimes comes up in these cases is you get into what people call like the bring me a rock scenario, right? Where they ask a question, we answer what we think it is they're asking, and then they're saying that's not what I asked, and we're like, okay, well, what is it, right? And then they ask the same question, and that's how we interpret it, and then they interpret us just giving them the same information over and over again. So it's a communication translational thing, and I think one way to think about it is, we're speaking Oklo reactor design speak, and they're speaking their historical experience speak, and making sure we build the right communication pathways and translation points. It takes time and it takes practice. Mostly it's practice. And that's where I think some of this maybe fell apart a little bit, right? We have information we present information in some cases that looks different than what they may be used to. It's still maybe full, but maybe they need more time to process it. Or maybe we need to spend more time walking through cross-mapping where that goes. Those are some of the things we see going forward that we're going to do. A lot of this gets back to, I think, making sure that, we support, I think, the sort of in-depth of communications and audits that can get these things best done. In other words, making sure that when we talk about these things, we're able to like fully, I would say, communicate on the same wavelength and the same language. And then part of that supported also by sort of crosswalking or cross-mapping what we're doing to what they've done before, to other things they've seen before. And I think that helps a lot. And that's something that, I think in hindsight, we see that there's some areas we can do more of that for sure. And that'll help us be a lot more successful. Now, I think the other part is like, we did tremendous things with them, right? Like, in other words, one thing that drives me a little crazy is people sometimes in this industry look at any sort of like stumble as failure. I think the failure is not trying, right, hard enough. And so for us, like, we tried. I mean, we swung for the fences and maybe we hit a triple, maybe we hit a double and we got called out rounding to third. But the reality is, like, we're going to be up to bat again here, and then we'll hit it out of the park. But we'll do what we need to do. But we got a lot done with them, and some really important items that I think together, the agency and us, like, we did good work to sort of prepare the way for us being successful with having a safe licensed reactor, and for others to come behind. But yeah, I mean, it's just the nature of it.
Were you guys able to come to a resolution on your like main philosophy? I remember reading some of the filings, the Maximumcredible accident. I thought that was such a smart way to approach it. Is there alignment on that? Are they willing to look at it from that perspective? And the way I'm going to paraphrase, and you tell me if I've got this right. Like Maximumcredible accident, you say, well, what's the worst that could happen? Let's look at the spread of source term. Let's look at its effect on people in the environment. Oh my God, even the worst thing that could happen under this scenario, it doesn't meet the threshold of harm. So let's do it. Let's get it through. Is that the basic idea of Maximumcredible accident? And maybe you could explain that to me a little bit.
Yeah, I mean, that's the thing. It's like what is the worst credible event that can happen that then challenges the plan? And then what are the impacts, right? And so what we did was sort of the root of this was we piloted this approach called the licensing modernization project, which was a risk-informed approach back in 2018. one of the lessons learned we had on that was sort of the basis of where that was at the time and where we were for application submittal. There was maybe some I would say some challenges or risks with going in with kind of a risk predicated approach like that for a new technology that was so small, because there's so little that can actually cause harm to people in a system like this.
Yeah, I mean, but this just drives me crazy. How come you can't just do it based on size? Like when I was in the drone industry, we went to the FAA and we lobbied for just, pick a size, any size, it doesn't matter, but pick a size even you can admit doesn't meet the threshold for harm. And they picked something like 2 pounds, and that ruled out certain business applications, but opened up a pathway for a tremendous amount of innovation in the tiny drone sector. Is that a discussion? Is that possible to just draw a threshold and say, hey, you tell us like how small is small enough that it doesn't need the same level of scrutiny?
Yeah, I think that's something that's emerging, but I think it just takes time, right? And I don't think there's enough people talking about this in a cohesive manner that recognize some of the aspects around really small reactors, micro reactors in particular.
But aren't you guys able to prove mathematically? Like, I would love to hear like your system, was it 1 or 2 megawatts?
Yeah, so we went in.
Like you only do so much source term. Like, how much could it possibly be?
Yeah, and that's the thing. It's funny, right? So we came up with this based on what we did in the pilot application, and then we coupled that with this source term analysis, which just assumed material releases arbitrarily, that just things vanish, right? So completely hypothetical. That sets a negative precedent because those things, that doesn't happen. Like material just doesn't disappear. But even in that case, it's a
but you can test the limits. That's a good way to test the
Exactly.
limits. I think that's an appropriate methodology. I think that's used cross industry. But so go on. What happened after you presented that case?
So we had that built in, but then when we did like our credibility thresholds, and when we did work that was trying to define what can actually happen to the plant, we could never get to a scenario that was anything even close to that, right?
Yeah.
And so what ends up happening then is they focus a lot on, okay, well, what's that line of credibility and where does that look? And
they shouldn't focus on it. If you already tested the limits, that doesn't make sense to focus on. That's the whole point of imagining the vanishing scenario.
Right. And that's where I think that's part of one of these disconnects, is how we do that. And so part of what happened in the pilot application was we showed, hey, like this is the methodologies as we implemented them. These are lessons learned. And then from that, NRC was like, hey, maybe some more deterministic, as they call them, or classical methods like the MCA may make more sense here. So we dove into that. And then and that's how we came up with then sort of taking that methodology of saying, okay, what's the worst thing that can happen? And that's credible. And then applying that forward with the sort of backstop, if you will, and here's this crazy hypothetical scenario. The thing was, we didn't want to lean on the hypothetical because we didn't want to set a negative precedent only. But this is sort of the lesson learned, is stitching these things together is somewhat tricky, because how do you walk from what you're saying is credible to then talking about something that's not credible? Does that, but in practice, I think what you're saying is exactly right. You have to look at this just from the sense of like, okay, even if I'm concerned about what might be credible or not, what's actually on the other threshold isn't, like on the other side of credible isn't even that bad, right?
Yeah.
And that's part of the part of where I think the conversation was actually getting to with the NRC. But in a way, we kind of ran out of time on it. So as we get to go back to it, that's one of the lessons learned, is helping stitch that together and helping them see, hey, here's sort of this like crazy hypothetical thing as a backstop, right? But here's why we see the MCA going in this way. But also, if you look at a sensitivity or an uncertainty around what's credible or not, you're still fine, because look, even if you just assume total artificial things, you can still be okay. But it's one of those things that we also stood on principles on, and we try not to give too much ground to going to beyond credible or non-credible things, because we think that could open the door for some negative precedent. And I think at the end of the day, we were pretty close. We're not that far apart. We got pretty close on this stuff. We just have to sort of go in and spend some more time familiarizing them with this. I think one thing that we also did is we took some very grotesque conservative assumptions, like neglecting all heat transfer off of the surface in one part, neglecting thermal radiation components of heat transfer. We did that as like bounding sensitivities. And then we tied that in with these like testing commitments that we were going to do before we started up the reactor, that demonstrated that the materials, that the fundamental properties of the system are what we've analyzed them to be. But what happened was this was a lost in translation thing, where I think what unfortunately came off in some cases was there was an interpretation, oh, well, Oklo didn't do the analysis in more rigor. They just took these grotesque assumptions. It was like, well, yeah, we did that because we can, because that illustrates how much margin we have. And it simplifies things. How
many people are you dealing with? Is it like a size of their team issue? I mean, is there like one person who's like a project manager that like you can get on, because these are complex topics, and and some of it is even philosophical. Is there a single person who once you come to a philosophical understanding can then work with his other teammates at the NRC to be like, you're the electrical guy. I know you love your electrical analysis, but we already philosophically showed how the electrical systems aren't even necessary for safety.
Yeah.
So you just don't need to look at the application. Like, is there a guy there that can do that for you?
I would say generally yes, but not all the time, right? And this is part of the human nature and some of the challenge of these things, right? These are multi-year reviews. You have people moving around, you have people being promoted out, you have competing priorities like Part 53 work. And I think the NRC did a lot of great work to try to do this as efficiently and as effectively as they could. But we did, I think, one of the things we did suffer from was a decent amount of turnover at that position you're talking about. So from right before we submitted the application until the time we got it denied, we went through 4 people in that position.
Oh my God.
And so, right, what happens?
Oh my God. So what are you going to do to prevent that from happening in this next round? Are they going to like help you guys figure that out?
Yeah, we've been very encouraged because I think NRC management recognizes that and they're really doing everything they can to ensure continuity. And on top of that, a lot of the people that already spent time with us are going to, generally be as involved as possible and available when we resubmit. So we're not necessarily having to restart from zero on this, but it's a constant risk, but at the end of the day, I think it's illuminated some of the mindset there, and hopefully it helps us navigate that and be very effective at that. So, it's one of those things you have to, it's just one of those things that exists, and you got to build in redundancy and talking to other people in the management chain. And so, that's one of the things that thankfully I think both the agency and us are focused on navigating, pretty well on that. And then just going back on the communications front, this is another thing where now that we've had one bite at the apple, we get to have some others, right? For example, like on the startup testing, we aren't using, I think we actually saw that as a big concession to the NRC, because we're saying, okay, you're going to get another chance. We're going to prove all the stuff's going to work the way we said it's going to work before we turn on, as a contingency to us turning on.
Yeah.
But I think what it got interpreted as was, Oklo's relying too much on testing and they're not doing the analysis. It's like, no. This is like, this is actually validating all the analysis. We're giving you another bite of the apple, so to speak.
Yeah.
So that's where some of these communication things are, and that's, I think the thing I look at
that as a case study, what do you do this next time around? Do you say we're not going to do the empirical studies? And
yeah, I think, we take what we've done and then we build on more with it, right? So we do a little bit more on uncertainty analyses with them to show it, and then we just make sure we communicate. This is that cross mapping, this communication, this translation of saying, hey, we're doing this for these reasons, and we're doing it for ourselves, and this is the benefit you get from it too. And I think it's just that kind of communication and repetition is going to really help solve that issue. And I think, if I could go back in time, what we would do differently before we submitted the application was spend more time from the time we decided we were going to do the MCA and the approaches we took, and then cross map sort of what we were doing to what we did in the pilot to what's been done before by other groups. That would have, I think, helped build those foundational sort of those language foundations and translational foundations, but basically a Rosetta Stone in a way, in the same way. And it's not because we're speaking in different terms. It's just, hey, when you look at through the lens of large operating light water reactors, then you get this little tiny metal fast reactor that comes in. It's different. So you got to learn to, we got to communicate on that front.
And has there been any thought to hedging risk across different regulators, and maybe even
Yes.
building the full system in another place and then bringing that data, the real hard data, back to the NRC?
Yes, more so now than ever.
Yeah.
I have confidence in the NRC, but one of the most interesting things that's happened in the last 2 months, I felt like one of the things we observed is we saw some international regulators saying like, cool to see what you're doing in the NRC, and we're excited to sort of follow that. Now, I think what we're seeing is more and more international regulators being like, this stuff's too important to wait. We got to do stuff.
Like Canada, right? Canada is trying to brand themselves as a leader in this space.
Yeah, I actually see as some other emerging countries being ones that are maybe better positioned, And I mean, I think, and they're, forgive me for speculating, but I imagine you're seeing some similar things, right?
Oh yeah, no, of course. I mean, this is what I do. I go around the world trying to see like what's a good environment to develop more nuclear. And then has there ever been thought, I mean, sure there's been thought, but maybe I would just love to hear your thoughts on, since you guys have such a small system, and to me, it seems like using some like this test the limit theory, some like gross conservative calculations, you could probably prove the safety of your system to a non-nuclear audience, just to like a well-versed mechanical audience. Has there been thought to going to a country that doesn't have a nuclear ecosystem, like Bermuda or Bahamas, or like somewhere like an island that needs it desperately? They've got some good mechanical engineers there. Hell, they license buildings that people's safety is like, they care about safety, but buildings can't collapse. And then just bring the mechanical engineering demonstration of safety to them. Can I hear your thoughts on that?
Yeah, I think that's actually some of the stuff exactly I'm alluding to. I see more interest emerging in those kind of areas with that kind of mentality, which is like, hey, yeah, we can build on just best practices in mechanical engineering. This is at the end of the day a heat transfer system, and what you're doing is analyzing, well, in a structural system, so you're analyzing the structural and heat transfer aspects with multiple redundant pathways that this can work.
Yeah.
It's honestly, this stuff's pretty easy to analyze. I mean, when we hire in folks from other fields, they work on way harder engineering problems. Just to be
I know.
blunt,
I know, and I know, and it's just so frustrating to me. Other regulators figure out how to do it without other industries regulators figure out how to guarantee safety without asking $1 billion worth of questions. And I know the NRC wants to do this as well. Like, I've met the people there, like a lot of them are very interested in like, hey, how can we do this more efficiently? So it seems to me like, yeah, there's like some sort of institutional issue that needs to be overcome, because I look at a small nuclear system, and it's like underground, right? Is your reactor underground? Yeah, a small nuclear system underground. And it's like, can't we just validate this from simple mechanical principles that this doesn't create a hazard to people or the environment now or forever? Like, and do that in a month? Like, other industries do this.
Yeah. No, it's true, and I think that's where I think there's a lot of procedural constraints, unfortunately, applied, I think, on the staff and on the NRC, both by Congress and by the fact that there are groups that weaponize the NRC against nuclear, right? I mean, that, like, look at the subsequent license renewal aspects and considerations that went on there. I mean, it's just this is the kind of stuff where I'm very hopeful that and the way I look at it, right, is like, hey, we took a shot on goal, and maybe we didn't score, we got the ball back, we're going to shoot again, we'll score, right? And that's great, that's fine, we'll get that done. But ideally, the experiences lined here pave the way forward for driving the right kinds of changes too. Obviously, we're learning from it and making the changes we need to do, but and we see the NRC doing that. We want to see them have even more capabilities afforded to them and driven to them by Congress and by sort of like, I mean, look at the fact that we have 2 empty commissioner seats. It'd be great to fill those. It'd be great to kind of get this stuff going as a priority, to recognize that you can guarantee I guess you can ensure adequate public safety and guarantee reasonable safety, right, in much more efficient ways than we have now. And I think the staff would thrive under environments that just operated more along some of those lines, and help them evaluate the full benefits and risks of the system, right? I mean, I think someone said,
does it require an act of Congress to create that framework for them to thrive? Like what could you do if you had $100 million in lobbying power? Could you make a law that freed up the NRC, people who want to see this change?
This is a great question. I think that's one piece, and then I think the other part is like, right, if, as a priority, just empowering the staff and the people there to drive these changes. Like, so I think that's a mix of providing them cover at the political levels, and by making sure they understand that we want transformation and modernization to thrive, because they've already done a lot of great work on that front. And I think Congress getting the parts of the Atomic Energy Act that have been either weaponized or are outdated or archaic or irrelevant out of their way, and getting them to actually look at the comprehensive societal risks and benefits of these things. I think that's where Congress could help drive that. But I think you kind of have to take a multi-pronged approach to get it to be as efficient as it could. Because again, I see really capable engineers, really smart people at the NRC who really get this stuff. I think we have great technical conversations. I mean, I can tell you, like, most of our favorite meetings are still with NRC staff. So, because it's engineering conversations, it's technical conversations, and it's it's more of the process and procedure stuff that causes, I think, the inefficiencies, and that I think can both be managed out and also, I think, legislated out, if that makes sense.
Yep. All right, we're running low on time, so I just want to make sure you get the final word on any thoughts, topics on your mind. Try to end on an optimistic note. That's the rule here.
Yeah. Oh, that's easy. I mean, I think at the end of the day, like, I mean, yeah, I guess I feel more optimistic in many ways than I've ever felt, even after, getting some of the news we got in January and facing an application denial. Because one, we've learned, we had the shot, right? We got that iteration under our belt, and now we get to go back, do it again, and we're better at it. The NRC learned from it. But I think what's really interesting is the fact that you have this global shift that's just accelerating with unprecedented speed in my experience, not just in the last year, but in the last month, a few weeks, honestly, about recognizing the importance of what's going on with this technology. And I think one thing that's really cool is we live in an era where people can actually understand what's actually happening and how these technologies really work and what the benefits they are afforded to them, without filters or biases or lenses afforded through, sort of the media or any other kind of like filtering mechanism. And I think it's creating this really exciting time where you're going to see, I think, the atom flourish in a way that we envisioned it doing, but we haven't fully seen, right? Like, and I mean, that's a great thing for humanity, right? Like but there's so much work to do that it's daunting, but that's a good thing because that just means there's opportunities that are almost too numerous to count. So I think it's a pretty exciting time.
Jake DeWitte, everybody.
And initiate at least a new approach to the many difficult problems that must be solved in both private and public conversation if the world is to shake off the inertia imposed by fear and is to make positive progress toward peace.